On tonight's programme, we look at the science behind the devastating earthquake in Japan and the tsunami it triggered. Dallas looks at how new earthquake-proof technology is keeping buildings standing.
So this basically just acts as a fuse. If it's kind of overloaded, then this bit is gonna go, and therefore the bridge is gonna be saved.
That's the theory.
Jem is back in his workshop explaining just how earthquakes happen.
All that twist and bend in the rock gets released into sudden movement. Like that.
And I visit the Pacific Tsunami Warning Center in Hawaii to see how early warning systems can save lives.
Magnitude 8.8 moment.
That's Bang Goes a Theory, revealing your world through science. Hello and welcome to Bang Goes the Theory. Now, on Friday morning, we all woke up to the terrible news that Japan had been hit by a devastating earthquake and tsunami, a very real reminder of the power of our planet.
That's right, at 2:46 in the afternoon, a truly enormous 8.9 magnitude earthquake struck near the east coast of Japan, triggering a tsunami that not only hit Japan, but spread across the entire Pacific towards Hawaii and the west coast of America.
At its source, the earthquake released 8,000 times more energy than the one that struck Christchurch in New Zealand in February. And the resultant tsunami caused devastation along the Japanese coastline and damage right the way across the Pacific.
Now, these shocking pictures of whole villages being swept away truly demonstrates how dynamic and destructive Earth can be. So far, thousands of lives have been lost, and the figure is expected to increase. One of the main reasons for the scale of casualties in Japan is that the earthquake's epicenter was very close to the coast. This gave people very little time to evacuate before the tsunami hit land, underlining how vital it is to issue warnings as early as possible. Now, back in January, I visited the Pacific Tsunami Warning Center in Hawaii to find out exactly how these early warning systems work. There's incredible heat coming off of this. Lots of water vapor and lots of sulfur dioxide. You can really smell it and it hits your eyes. On the southern coast of Hawaii's Big Island, the volcano Kilauea constantly spews its lava into the Pacific Ocean. It's the most active volcano in the world. Since 1953, it's erupted 33 times, and it's been non-stop for the last 18 years. It's so hot right here. Streams of 1,000 degrees Celsius lava pouring into the sea. This is Kilauea in all her glory. The lava from this volcano isn't the only threat here. Along the coast of the island, unstable volcanic rock can crash into the ocean, causing another destructive force of nature, the tsunami. Small tsunamis like those caused by landslides happen at least twice a year across the globe, but much larger ones can occur every 15 years or so, and they are caused by huge earthquakes at the bottom of the sea. Now, ordinary waves like these are created by the wind, and even though they look fairly tame today, they've still definitely got the power to knock me over. But add something like an earthquake, and you're talking about a wave with a different kind of power altogether. Whoop! So how exactly are tsunamis different from ordinary waves? Surprisingly, it's not about their size, it's how fast and how far apart they are. Here's an ordinary wave. Now, the distance between each crest, or the wavelength, is usually about 100 to 200 meters. When an earthquake occurs, the sea floor is deformed. That displaces the body of water above it. And as this body of water attempts to regain equilibrium, you get your tsunami wave. The distance between each crest increases to anything up to 300 miles. Out in the deep ocean, a tsunami wave is only a meter or so high, but it can travel up to 600 miles an hour. It can hit land peak first or trough first, which looks like a sudden low tide. But crucially, as the wave approaches the shore and the water depth decreases, the speed of the wave also decreases. But that energy has to go somewhere. So instead, the height of the wave begins to increase. To 30 meters or more, the wave moves inland, anything up to 1 or 2 miles, and takes everything with it in its path. And sometimes the second wave, which can be anything up to 2 hours away, can be even more powerful than the first.
Hawaii has been hit by at least 50 tsunamis since records began, and after 159 people were killed in 1946, the islands established their own tsunami warning center. It's one of just 3 in the entire world. And after the tragic tsunami of Boxing Day 2004, it took on a truly international role.
So these are seismometers all over the Earth. And up here on the screen above, this is seismometers that have actually seen something. Right now, we just have one white dot here in Southern California. If there were a big earthquake, we would suddenly see a whole bunch of white dots. And then as the energy spreads out across the Earth, you would see all of these dots would light up.
So you've got a 7.8 on the Richter scale. What happens next here?
My pager goes off. So I come running in here and I go and look at this screen over here.
Oh, wow, okay.
Each of these traces would suddenly show something, and basically the stream would go black. And we have to tell people when the tsunami is going to arrive.
How do you calculate that? Does the computer do it
where
for
we
you?
know where the earthquake is, so we
Yeah.
come over here. We know how fast the tsunami travels, because that depends only on water depth, so we can compute how fast the tsunami is going to travel and when it's going to arrive at various places. So the tsunami is going to be in 1 hour, 2 hours, 3 hours.
And there's Hawaii.
And it's going to take 15 hours to get to Hawaii.
These predictions are aided by pressure sensors throughout the Pacific, which allow the precise course of a tsunami to be tracked. 38 buoys dotted across the ocean pick up signals from sensors on the seabed and relay them back by satellite to the center in Hawaii. And once they've adjusted their predictions, the center issues warnings, not just to Hawaiians, but to people at risk all over the world.
Truly a magnitude 8.8 moment.
With every tsunami detected, whatever the size, Gerard collects new data which he hopes will make their predictions even more accurate the next time a very big tsunami hits.
The size of the 2004 earthquake, it's a magnitude 9.2 or 9.3 earthquake, a real monster.
Yeah.
The chances of that happening again are very good. I mean, in all probability, it will be in the Pacific for the simple reason that the Pacific has most earthquakes, period.
Yeah.
For the Pacific, the 2004 tsunami was actually a godsend because it reminded us of the hazard, and we realized we're not ready.
Okay.
And so there was an immediate scramble, and the system was greatly improved. And we've got to the point now where we think we're ready.
How right Gerard was. Even so, this weekend has been an incredible test for his team, with hundreds of thousands of lives across the Pacific depending on their response to the earthquake. Gerard had hardly slept since it struck, but late on Saturday night, we managed to get him on the phone to hear exactly how they managed.
Initially, it seemed like it was only a magnitude 7.9. That was enough to get our initial messages out. Very soon after that, we got the first seafloor reading of how big the tsunami was, and that measured a meter of water level variation out on the deep ocean, which is huge. We issued warnings to Japan and Russia in our initial message, and then as soon as we saw that it was big, it went Pacific-wide. The tsunami traveled across the ocean, and it reflected off one continent and traveled back across the ocean. You can think of it as the entire ocean surface quivering because the earthquake kicked it. It's over now, although the ocean is still oscillating. I would guess that hundreds of thousands of people moved as a consequence of the warning. If it hadn't been for the great tragedy of 2004, we would not have been as prepared. I have no doubts about that at all.
Japan have their own warning system. It's very effective indeed. In fact, seismometers were picking up 4 shocks a couple of days before the earthquake. Now, obviously, we still can't predict exactly when an earthquake is going to hit. But once it did hit, they were able to issue a tsunami warning 3 minutes after the earthquake. That's very effective. And then the tsunami, unfortunately, hit 15 minutes after the earthquake. So that's a very, very short window in which to work in. But they initiated a full coastal evacuation and really did the best they could.
Well, that's the thing. It's the best we can do. And until science gets to a level where we can predict an earthquake's going to happen and the consequent tsunami, we're left in a situation where the best we can do is detect a tsunami when it just starts and then try and warn people in time. But it's not an easy situation at all.
It's really not, but the science is getting better all the time. I mean, with regards to the tsunami, all of this data from the Japan earthquake and tsunami is going to be fed into the warning systems, modelled, so we can better understand the course, speed, physics of a tsunami wave. In other words, they can now decide whether it's really necessary to carry out a full coastal evacuation or a partial one, you know. So that's getting better all the time.
It's getting better, but natural phenomena by their nature are complex and unpredictable. Obviously, much more on all this on our website, and if you want to follow the conversation, join in the conversation, you can on Twitter at BBC Bang. Now, you will have noticed we're obviously not in our Bang HQ. We're actually right in the middle of doing the Bang Goes a Theory live, and we're in London at the Big Bang Fair, but really the events of last Friday kind of overtook us. But we really kind of wanted to get to the bottom of all of this. Let's just talk about the numbers for a minute. This was a magnitude 8.9 event. By comparison, a magnitude 9 earthquake would be the equivalent of the entire UK's annual energy use in a single event.
So we're saying like every nuclear power station, every coal-fired one, every gas-fired one, all working for a year.
Boom, like that.
In one event. And Jem, can we talk a little bit about the maths behind all of this? How do you go about measuring the magnitude of an earthquake?
It gets a little confusing, but generally what's quoted are numbers off the Richter scale. Okay? And the way that they're worked out is you've got a seismograph, which is like a pen on a piece of paper, and when the Earth moves, it moves. And so you end up with this wavy traced line, okay? And then by knowing how far your seismograph is from the center of the quake and knowing the size of your wavy line, you can work out where you are on the Richter scale, like how much Earth movement would have happened there. Now, the interesting thing is, it's not a simple scale in the sense that if you get another earthquake from that same place and your trace is 10 times bigger, you'll move up 1 on the Richter scale. If you get a trace that's 100 times bigger, you'll move up 2 on the Richter scale.
So it's an exponential increase. It's not like just turning up the volume knob a little bit.
No, it's like if you've got a 6, an earthquake that's a 6 on that scale, and then one comes in that's a 7, that's 10 times bigger. If one comes in that's an 8, it's 10 times 10 times bigger, 100 times bigger. But what I wanted to get into was, what's the mechanism of a tsunami causing earthquake? And it was a sudden movement that happened 24 kilometers below the ocean, the subduction zone of the Japanese trench. But what does that mean? Well, I went to the workshop to see if I could paint a clearer picture. Earthquakes are caused by the movement of the huge tectonic plates that continents sit on. And what happens is they come together, and one, in this case, the Pacific plate, is moving below the Japanese or Eurasian plate. Now, it causes that plate to bend when it sticks there. There'll be a bit too much friction, it'll stick, pressure builds up until suddenly it's released and flick. Have a look at this. Now, this is the tectonic plate that Japan is sat on, and here's the Pacific plate coming down underneath it. Now, normally they want to move together at about 9 centimeters a year, but sometimes they get stuck. And when they get stuck, the energy of them moving together gets translated to strain energy, literally flex and bend in these huge slabs of rock. Now, that energy builds and builds. They're flexing and bending more and more. When they finally slip, that stored energy, all that twist and bend in the rock, gets released into sudden movement, like that. As you can see, it literally flicks up, moving the ocean floor above it, which moves the ocean, causing a tsunami. So here we've got a bigger submarine version of what's going on. Now, this gives a representation of what's been happening 24 kilometers below the ocean surface in the Japan Trench. And these things work in what they call a stick-slip way. Most of the time, they're stuck, but occasionally they slip. And that's what an earthquake is. So we've got it here. This is bent up here. It's full of pent-up energy, waiting to slip. Now, when the slip happens, that energy gets released into the ocean, causing a series of tsunami waves, moving in both directions across the Pacific.
It's interesting, actually, looking at the news footage over Friday and the weekend, because even though it was obviously a massive, massive earthquake, it seemed it was the tsunami wave itself that was causing most of the damage.
Yeah. I saw a report of a guy who was stuck in a building and he felt it rock and sway a heck of a lot, but then it settled back down again.
Well, if you think about, Japan in terms of how they build their buildings, because they have such a history of earthquakes, they've got very, very good at earthquake-proofing their buildings, as have the Californians, that other earthquake hotspot, as I went to find out. The San Andreas Fault. It's the line where two of the Earth's tectonic plates meet and rub up against each other. All the land over there is moving northwards at an eye-watering 55 millimeters per year on average, which means if I waited here for, 15 million years or so, I'd see Los Angeles gently passing me by northwards to where Alaska is today. Unfortunately, all this geological rubbing can result in major earthquakes. I spent a bit of time living in Los Angeles, and I often wondered if today was the day I was going to experience the earthquake everyone dreads, what they call the big one, a magnitude 7 on the famous Richter scale. In LA, people take this threat very seriously. This truck is designed to give people the experience of a major earthquake without it actually injuring them. I'll admit I'm a little nervous, so I've enlisted an earthquake expert to sit in with me and hold my hand.
Welcome to California, earthquake country.
Thank you very much.
How are you feeling?
Slightly sweaty palms, a bit nervous, not quite sure what to expect. I mean, what sort of number on the Richter scale would you have to be to actually sort of perceive an earthquake?
You could start feeling them at magnitude 3, depending on what kind of rock you're on, how close you are to where the fault moved. I think it would be good if you put on some of these safety glasses.
Oh, really? It's going to be that?
Well, you never can tell. Better to be safe. That's the idea.
Okay.
All right, we're ready.
So wow. Okay, so that's quite violent. My tea's almost snapping.
A typical Southern California earthquake. Magnitude maybe 4.5 or so.
Wow.
Very, very much like what just happened here in the last few days. We had a 4.7 and 4.1. This is that experience if you were near the earthquake site.
So you actually had one of these, that sort of level recently?
Exactly.
Okay. Wow, okay, this is much bigger. Where are we now?
Around 7.5 now. This is where buildings collapse. This is where people get killed. This is the big one.
Okay, stop! Turn it off! Turn it off! Turn it off! Well, that was alarming, but it does make Californians take earthquake resistance very seriously, particularly in the design and engineering of bridges that are the lifelines to major cities. Because when a big one really does hit, there'll be no reaching for the off button. Somewhere that Californians know that only too well is here in San Francisco. Just over a century ago, the city was shaken to its foundations by a magnitude 8 earthquake that killed 3,000 people and left over 200,000 homeless. And then in 1989, it was hit by another massive earthquake. At magnitude 6.9, it claimed 63 lives. And the city's Bay Bridge, little brother to the more famous Golden Gate Bridge, was one fatal location. Believe it or not, but the bridge is actually built on wooden pilings, Douglas fir trees that are driven into the bay mud. And it's really hats off to the designers and the engineers that this bridge has lasted so long. But after 80 years, it's time to replace it. And currently, under construction, is a new Bay Bridge. And naturally, earthquake protection is at the forefront of its design. To cope with the way that earthquakes can make the ground behave more like a liquid than a solid, the bridge has been built with very strong footings that splay out 100 meters deep into the mud below. It's just one feature that means this remarkable bridge will withstand that 7.5 magnitude earthquake and, more importantly, be able to stay open afterwards.
In the event of a big earthquake, what is it about the engineering of this bridge that's special?
Well, this bridge is built to what we call lifeline criteria. And basically what that means is that after a large-scale earthquake, this bridge will remain immediately available to emergency service vehicles like fire trucks, police, and then without having to do a complete rebuild, we'll be able to open it back up to public service.
This $5 billion bridge is being engineered to withstand a freak earthquake, the likes of which might only be seen once in 1,500 years. One way to do that is by building the bridge in sections with a gap between them that allows for free movement.
Wow, this is amazing. So really, we're at a junction point between two completely separate bridges here. Why can't you just have one long bridge? Why do you need these spaces at all?
If you don't have the bridge broken up into sections in an earthquake, it can potentially cause a lot of damage.
So if you can imagine we're in a big earthquake situation now, what would actually be going on here?
These two bridges are going to hit each other. The first thing that will happen is that sort of rubberized grommet there will take the first impact. And then this hinge pipe beam will allow the bridge to move in and out.
Almost a bit like doweling when you're putting your IKEA furniture together. That's sort of how they work as connectors.
Well, that's a fantastic analogy. That's exactly what they're doing. We don't want the bridges to skew or move sideways because you'll never get them back together. So the pipe beams keep the bridge together like this, and all of the energy will be transferred into what we call a fuse, this piece right here.
So this basically just acts as a fuse. If it's kind of overloaded, then this bit is gonna go, and therefore the bridge is going to be saved.
That's the theory.
A similar device can be found up the bridge's one and only tower, which will support the road below.
So I'm 65 meters up in the very heart of the tower. It's actually not one tower. There's four completely independent legs, which are joined together by these connecting beams, which you might be able to see if you come down here. Now, these beams, obviously, on a non-earthquake day like today, are going to give the whole bridge its strength, its rigidity, but they're also designed to bow and flex. And if the earthquake's bad enough, those beams can actually buckle. And the clever bit is that whole section can be removed and replaced with these bolts here. You can see how they just unscrew, and you can put a whole new section on.
4 legs are better than one in an earthquake, because if one breaks, the others will be strong enough to keep the bridge up. It's due to be completed in 2013, but to get an idea of what it's actually going to look like, I'm going to take a look from the very top.
How high are we going?
112 meters above the water.
112 meters above the water, so this is not for the faint-hearted. You're not faint-hearted.
No, I'm
He's
not.
all right, he's all right, good. If you get worried, if you get a bit nervous, then I'm here for you, okay?
All right, I appreciate that.
Well, I tell you what, you've got to have a head for heights for this. So just to take stock for a little bit, over that way towards San Francisco is the San Andreas fault, which is capable of serving up a sort of magnitude 8.1 earthquake. Over there, towards Berkeley, is the Hayward fault, which is capable of serving up a 7.1 magnitude earthquake. And I'm right in the middle. And it's a question of not if, but when. According to the US Geological Survey, there's a 70% chance of a big earthquake striking right here sometime in the next 20 years. But at least for the 280,000 people who drive across there every day, it's reassuring to know at least their bridge will be safe.
That is a beautiful bridge, and what a feat of engineering.
Well, it really is. If you're going to build a bridge in, in an earthquake area like San Francisco, it's got to be. But also in Japan, they've got similar kinds of earthquake-proof innovations going on. For example, they've actually been lifting some of the buildings off the ground and placing these rubber bearings and dampeners underneath, exactly like a shock absorber, to absorb the vibrations. And some of them even have like metal plates underneath. You imagine that's the building there, so the earth moving underneath.
Amazing.
And the building will stay where it is. Really, really interesting. interesting.
Genius.
I love that.
Yeah.
One of the few sort of positives I could take from the footage that I've seen is, despite the amount the Earth was moving,
Yeah.
a lot of those buildings remain structurally sound.
Absolutely.
I mean, it's all credit to Japanese engineering.
Absolutely. Now, guys, we have run out of time. We're going to have to say goodbye.
Make sure you check out our website if you want more information on tonight's show. While you're there, look at the National Science and Engineering Week. Lots of events going on all around the UK. As ever, all details on /bang.
Plus, follow the links to the Open University for a load more amazing science. And check out the dates and details of our new live show. All summer, we'll be touring the country, bringing hands-on science to a town near you.
We will indeed. We'll see you next week.
We will. OK, that is enough of that. We have run out of time. We will see you soon. Goodbye.
Bye.
Bye.
The team are back next Monday at 7:30. And stand by for details of the Bang Roadshow to follow. Well, on the way next on BBC One, EastEnders.